Uh, Greetings, everyone. Let us start the third session for the course Semiconductor Devices and Circuits. The course is being taught by Professor Sanjeev Sambandhan, and I am TAing the course. And this is our third live session. So let me start with the problem first of that was given to you people in assignment 1, and it states that if we have a wave function of the particle, it must be normalizable, and you were you were asked to, let me repeat, this is the question 1 from assignment first. Where you had been asked to give the reason that if a wave function is given, it must be normalizable. So you were asked to choose one of the four options, and it is simple that if we have a wave function must uh, exist somewhere in the space. That's it has some finite probability of occurrence between the interval minus infinity to infinity dx equal to 1. So it seems that option C is the correct option. So we will take option C. Now let's move to the second question. Question number 2, where we were given four wave functions as can be seen in the figure. They where psi is shown, and we can clearly see that they we have to use some basic properties of wave functions here. We know that the wave function must exist somewhere, and that condition is satisfied over here, but also the wave function has to be continuous. Now let us see whether they are continuous or not. Clearly this over here is not continuous. Am I correct? No, this is continuous absolutely. As you can see, while I draw this, my pen will not lift. So simply this A is continuous. The second option over here, as we can see, this is also continuous, and third also is continuous. But if we look at the option 4, it is showing discontinuity at x equal to 0. So we can easily see that this option 4 is not the physically realizable quantum mechanical wave function. So we will take the option 4. Now if we move towards the third problem that was asked in the assignment, it states that if uh, if we have two interference patterns with the maximum and minimum intensities of the ratio of 25:1, what is the ratio of the amplitude of these two interfering waves? So we know, as taught by the professor in lecture, this intensity is given, where this is the net intensity, is given simply by individual intensities summed with a phase factor cos of phi. But we also know that this intensity is directly proportional to the amplitude square. So so if we now see and write this intensity in terms of amplitudes, we will write it to be A1 squared plus A2 squared plus 2 times A1 squared A2 squared, when this will be under the square root cos of phi. This will simplify to A1 squared plus A2 squared plus 2 times A1 A2 cos phi. This is as simple. So we have got uh, now two conditions on the intensities, where one condition is that the intensity is maximum and the other condition is that this intensity is minimum. Now we know that this cos of phi will be having its maximum value 1 at phi equal to 0, and it will be having the value of minus 1 at cos of at theta or phi equal to minus 180 degree, and it will be minus 1. So if I write it like this for maximum intensity, this phi will be equal to 0 degrees, and for minimum intensity this phi will be equal to 180 degrees. So we can write this I now as I max when it is cos of 0 degrees. It will be simply A1 square plus A2 square plus A2 squared plus 2 times A1 A2 cos of 0, and we know this will be 1, cos of 0 will be 1, so this will simply be A1 squared plus A2 squared plus 2 times A1 A2. So this maximum intensity, we know this can be written as A1 plus A2 whole squared. So this maximum intensity is simply the square of the sum of the amplitudes. Now for the minimum intensity, we can write I minimum equal to A1 squared plus A2 squared plus 2 times A1 A2 cos of 180 degrees, and this will simply be equal to A1 squared plus A2 squared plus 2 times A1 A2 into minus 1. So this will become A1 squared plus A2 squared plus 2 times, let me bring the minus in front, minus times A1 A2, or simply it will become A1 minus A2 whole squared. This is the minimum intensity, but we were given the ratio of these maximum and minimum intensities to be equal to 25:1. So from these two relations, what we got, I max by I min was the A1 plus A2 whole squared divided by A1 minus A2 whole squared. So we know that this ratio is given by 25:1, and this will be A1 plus A2 whole squared divided by A1 minus A2 whole squared. So if we take the square root, we will be left with 5:1 equal to A1 plus A2 divided by A1 minus A2, or it will simply be 5 times A1 minus 5 times A2 equals A1 plus A2, or simply 4 times A1 equals 6 times A2, or A1 by A2 is equal to 3 by 2 or equal to 1.5. Let us see which option it was. It was option B. So we will choose option B. Now we have seen this third problem as well. We have solved it numerically. Now if we move towards the fourth problem, it states that in electron beam lithography patterns, they are exposed with electrons, and the wavelength of electrons helps to achieve some feature size which is of the order of the nanometers, and it is given that this electron gun has energy of 15 kilo electron volts, and we are required to find the wavelength of these electrons, and we are given the mass and the Planck's constant as well, and it has been said that we have to neglect the relativistic effects. So if we start this problem with by writing these constants, what we are given, we are given the energy to be equal to 50 kilo electron volts, and we know that E is given by, this kinetic energy is given by P square by 2 m naught, and this P itself is given by h by lambda, where this h is the Planck's constant. Now if we substitute this P in here, we will get E equal to h squared by 2 m naught lambda squared. Since we are given the value of E, we will write it in terms of E itself. The lambda will become h by 2 m naught E square root. Now let us uh, substitute the values for these, as h is given to be equal to, 6.626 into 10 raised power minus 34, and the effective mass is given to be equal to 9.109 into 10 raised power minus 31, and the energy was given to be 50 kilo electron volts, and we have to convert it into the joules because h bar is in the units of joule. 10 to the power 3 into, let's multiply by the electronic charge so that we will convert it into the joules, 10 raised power minus 19. So if we now evaluate this will simply be 6.626 into 10 raised power minus 34, and in numerator we will be left with 2 into 9.109 into 1.6, it will be equal to 145.744 into 10 raised power minus 46. Now 6.626 into 10 raised power minus 34, taking the square root of the denominator, it will give us 12.072 into 10 raised power minus 23, or simply we will divide these two to get it to be equal to 0.55 into 10 raised power minus 11. Now let's check. Since we are required in options, it's given the answer has to be in nanometers. This we got in meters. We will convert it into nanometers by simply writing it to be 0.0055 into 10 raised power minus 9 meters, or the answer is simply 0.0055 nanometer. So the option which seems correct here is option D. Now, if we move towards another problem, it states that we have an electron which is in one-dimensional potential well, and it jumps from the n equal to 4 energy level to the ground state energy level, and while doing so, it emits a photon of wavelength 20.9 nanometers. So we are asked to find the width of the well, and also it has been given us to assume the electronic effective mass and the Planck's constant. Now we know for the particle in one dimension, the energy E for the nth state, if we consider the nth state, the energy is given by n square pi square h bar squared over 2m L square, where this L is the length of the box in 1D. We are given that n is equal to 4, and for another n, we are required to find the ground state energy. And we know in here, for ground state energy, n is equal to 1, because n equal to 0 will give the wave function to be the 0. That's what we had seen in the lectures as well. The ground state energy will be corresponding to n equal to 1 for ground state. So now it's simple. We will simply write the energy at the fourth state, and it will be simply equal to 4 squared pi squared h bar squared by 2m L squared. And also we are given that E1 will be now 1 squared h bar squared pi squared by 2m L squared. If now we see that this electron jumps from the fourth energy level to the first energy level, it transits from E4 to E1. So it's simple. We will be writing the energy difference delta E equal to E4 minus E1 equal to 4 squared minus 1 squared pi squared h bar squared by 2ml squared. So we have seen that by simply transiting from the fourth energy state to the first energy state, we have got the energy difference. Okay, so now this difference will simply be equal to 16 minus 1 will be 15 pi square h bar squared by 2ml square. That's the energy difference that we got while they were transiting. So we know that in the question it is given, we are given simply the wavelength. So let's write this energy in terms of the wavelength. We know that this delta E, which will be given by h nu, and nu is the frequency, will be given by hc by lambda, and this lambda, we can substitute these values in the first expression, and we will get it to be hc by lambda to be equal to 15 pi squared h bar squared by 2m L squared. So now we know that this h bar, we can write it to be h bar is h by 2 pi. So this will become hc by lambda equal to 15 pi squared h squared by 4 pi squared by 2 2ml squared. This pi square and pi this pi square and this pi square will go, and we will simply be cancelling this h bar and this h1h over here, and we will be getting this equal to c by lambda equal to 15h by 8ml square. 15h by 8ml squared. Now, since we are required to find this width of this well, which is the 1D potential well, we will simply transfer this L on the other side, and it will become 15H lambda by 8mc. Now let us substitute the values for the h lambda mass and the velocity of the light. We know that this will be 15 into value of h is 6.626 into 10 raised to power minus 34 joule second. 6.626 into 26 into 10 raised to power minus 34 joule second, and this is 8 into, since it is 9.1, it is 9.11 into 10 raised to power minus 31 into the velocity of light, 3 into 10 raised to power 8, and all this will be under the square root. Now let me calculate it. It comes out to be equal to 9.5007 into 10 raised to power of minus 20. So if we now square root this, we will get it to be equal to 3.08 into 10 raised to power minus 10 meters. This will be the width. Since we are required to find in the nanometers, we will simply write it in nanometers to be equal to 0.308 into 10 raised to power minus 9 meters, or simply L is equal to 0.308 nanometers. So this is our answer, and now let us see which option does it match. It matched with option B. So option B is the correct option to select here. Now let's see sixth problem. It states that the wave function psi of x is given, and it is given to be 0 if x is less than 0, and it only exists between the limits 0 to L. So we are required to find the normalization constant A. As simple as that. So if we see, we know that this a particle must lie somewhere in space. We will be integrating it between minus infinity to infinity psi of x, since this is only in one dimension, x psi of x dx squared equal to 1. Now we know that this wave function only exists between 0 to L. This wave function exists only between 0 to L, we will write simply is this equal to a root 30 and its conjugate will be the expression itself into a into root 30 x into L minus x dx equals 1. And this simply means taking the constants out, this will be a squared, 30 times a squared, and this will be x squared L minus x squared with integral over 0 to L dx equal to 1. Now, if we solve this integral by doing the integration by parts, that will be much easier. So let me approach it by integration by parts. So if we see, it will become 30 times a squared, uh, 0 to L x squared, it will become minus of x squared L minus x cubed by 3 with its limits between 0 to L. This will become plus derivating the 2x square, it will become 2x, and taking the constant out, this 3, this will be 2 times 2 by 3, 0 to L dx, L minus x cube dx equals 1. So if I now put the limits in here, I know that if I put it x to be L, this and this will go, and it will be I will be left with 0. And if I put x equal to 0, and this will simply be 0. So this expression overall is simply 0. Now if we solve the other part of this integral by doing the integration by parts, again, we will simply derivate this x, and we will get it to be equal to, once again, we will get it equal to 30 times a squared, and this will simply be equal to minus times 2 by 3 x times minus times L minus x raised power 4 by 4 with its limits between 0 to L, and the other half will look like simply 2 by 3 derivating this x, we will be left with L minus x 4 simple, and its minus will go with minus, it will become plus, it will be L minus x to the power 4 by 4 with its integration limits between 0 to L dx equals 1. As simple as that. Now if we see this using the same logic as previously, putting the limit L over here, this will become 0, and when I put the limit 0 over here, it will become 0 in that case as well. So this expression will become 0 simply. I will be left with 30a squared. Let me write it down again. 30a squared, and it is 2 by 3 with limits between 0 to L, L minus x to the power 4 by 4. Let's take it to be 4 dx equal to 1. Now this 3 will cancel with this, it will be 10. I will be left with 20a squared divided by 4. 0 to L will simply give me L minus x to the power 5 by 5 with limits between 0 to L equal to 1. So now if I put the limit L it will simply vanish, and when I put the limit 0, it will give me L to the power 5 by 5. So this is a squared. 20 by 4 will be 5 equal to 1. This will simply go, and I will be left with L to the power 5 a square equal to 1, or simply a square equal to 1 by L to the power 5, or a is equal to L to the power minus 5 by 2. So now let us see which option it was. It was option A. So option A seems to be the right one, and we had to select option A. Now let's move to the seventh problem. It states that we have an electron which lies in the 1D potential well, and its width along the x-axis is given to be equal to 7.3 nanometers, and we are also given that this electron it is in the third state, that the is equal to 3, and we are required to find the probability of this electron per unit length at x equal to zero point 0.3 nanometers. So it is simple. We are given the values of L equal to 7.3 nanometer. We are given N is equal to 3. Also, we are given X equal to zero point 0.3 nanometers. So we know this nth wave function, this nth wave function, we can write that solution sine n of x that we have seen in previous live sessions as well. It is simply equal to root of 2 by L sine of n pi by L x. So this is the simple solution for the nth state. Now we are required to find the probability. This probability will simply be given by psi n of x squared. Actually, it's psi n conjugate into psi n. So it will simply be root of 2 by L sine of n pi x by L into root of 2 by L sine of n pi x by L. Now this probability, that is denoted by P, will be given by 2 by L, 2 by L sine square n pi by L x. Now we know that this L and this n, the values of these are given, and this n and L is given to be equal to 7.3 nanometer, 7.3 nanometer minus 9 meters sine square, n is given to be equal to 3 pi by L, 7.3 into 10 raised to power minus 9, and x is given to be equal to zero point 0.3 nanometer. So it is as simple. Now if we solve this on the calculator, this will simply be equal to, let me write its value, So it will simply come out to be equal to point 142, and if I now divide these 2 into 0.142 divided by 7.3 into 10 raised power minus 9, it will simply come out to be 2 divided by 2. It will simply come out to be 0.0389 divided by 10 raised power minus 9 meters. So the answer, since it asks the probability to be the in the units of per unit nanometer length, so it will be equal to simply P will simply be equal to 0.0389. So we must choose the, since it's closest to the 0.039, we will simply write it to be equal to option A. So we have now seen that this simply gave us the probability to be equal to 0.039, which is very less. Now if we move towards the eighth problem, and this eighth problem, it states that the electrons, they are being accelerated through an potential, electric potential V, and they are allowed to fall on a pair of slits, and the separation between these slits is 100 nanometer, and this results in the pattern formation, and that interference pattern, it indicates that the electrons are having the wavelength of 1 nanometer. Now we are asked to find this electric potential that gave that much amount of energy to these electrons. And also in part 2 we are told to find that if we are passing through these slits, what is the minimum spread in the momentum. So we will be simply using Heisenberg's uncertainty principle there. Now if I solve this, now I will see what I have been given. I have been given lambda equal to 1 nanometer, and I know that the relation between the lambda and the energy, so I will simply use that and solve this expression. So the energy, if I use the simple, I will use the energy balance, that is this energy, this potential energy will the potential V will reflect in terms of the kinetic energy of these electrons. I will simply say that this Q times V, the energy provided by these external potential with magnitude V, will simply be equal to P square by 2m. So this is simple, and we know that this P is equal to h by lambda, and we know that the values of m is given and also value of h is given. We will simply find the expression for V. It will simply be given by V equal to P square will be h square by 2m lambda squared q. So if I put these values, it will be 6.626 into 10 raised power minus 34 squared divided by 2 into 9.11 into 10 raised power minus 31. Lambda squared will be 1 nanometer will be simply equal to 10 to the power minus 9 meters squared, and since we are required to multiply with the electronic charge, this electronic charge is having the value of 1.6 into 10 raised power minus 19 coulombs. So it's simple. Now we need to solve this expression to get the value for V. It will simply be equal to 6.626 43 43.9038 into 10 raised power minus 68 divided by 2 into 9.11 into 6, simply 29.152 into 10 raised power minus 68 is V. So this V is equal to the division of these two, 43.9038 divided by 29.152, and it will simply come out to be 1.506 volts. So we can write it to be equal to approximately 1.5 volts. So this V is 1.5 volts. So option C uh, for part first only matches till now. Now we are required to find the uh, split in the spread in the electrons momentum, and we will be simply using the Heisenberg's uncertainty principle. We will be simply using the Heisenberg's uncertainty principle, which states that we cannot find the position and the momentum simultaneously. There is some error associated with both. So if this is the delta x, this uncertainty is position, and this uncertainty in momentum, this must be equal, greater or equal to h bar by 2. So simply we know that this spread separation was given to be equal to 100 nanometer. We can write this delta x is equal to 100 nanometers. So simply this will be equal to delta px is greater or equal to h bar by 2 times delta x, or this delta px is greater or equal to h bar, which with this h bar is h by 2 pi, which is 6.626 into 10 raised power minus 34 divided by 2 into 100 nanometer, and this 100 nanometer will be 100 into 10 raised power minus 9. Since this was h bar, I have written h, I will be dividing by 2 pi. This will be simply the value for this uncertainty in the momentum. So if I calculate this value, it will come out to be equal to 5.2728 into 10 raised power minus 28. Let us write down its units as well. It will be kg meter per second. So now let us see which option matches. It is 10.54. So we will be going with option D. It's simple because only option this first option matched, that's the 1.5 volts, which was the required electric potential, and the second half, which stated the minimum potential, it didn't match. So we are going with option D, which is none of these. Now if we move to another problem from the assignments, it was that if we have a wave function which is having the wave function given by root 3 cos of 2 pi x by a between the limits minus a by 2 to a by 2, what is the average momentum of this particle in the nth state? So if I now solve this, we have been given this momentum. We know this momentum operator. If we see, this momentum operator was given by minus I times h bar d by dx. Now we are required to find the average momentum over here. So the average momentum, average momentum, average momentum will simply be equal to p of x between the limits minus infinity to infinity. They are normal. Uh, what we used was the psi star p of x, where this is the momentum operator psi dx. So this will be the average momentum, and this average is denoted by these kind of brackets. So now let us put the value for this psi star. We know this only lies between minus a by 2 to plus a by 2, and psi star is root 3 cos of 2 pi x by a into minus times iota h bar d by dx of this psi. Psi is simply root 3 cos of 2 pi x by a dx. So we are required to derivate this first. This will simply be minus a by 2 to plus a by 2, taking the constants out. Root 3 and root 3 multiplied will give us 3, and this will be minus iota h bar, simply with the limits minus a by 2 to plus a by 2 cos of 2 pi by a x, and we know the derivative of this cos will simply be minus 2 pi by a sine of 2 pi by a of x with limits with, limits between minus a by 2 to plus a by 2. Now taking the constants out again, it will be 6 times, it will become iota h bar 6 times pi by 2, 6 times pi by a, sorry, 6 times pi by a with the limits between minus a by 2 to plus a by 2, and we are left with cos of 2 pi by a and sine of 2 pi by a. Cos of 2 pi by a x sine of 2 pi by a x dx. Now let us use the simple identity where we know sine of 2 theta is 2 times sine theta cos theta. So if I do that, multiply this by 2 and divide by 2, it will simply be iota h bar. This 2 will cancel out with this, and we will be left with 3 pi by a, and this will be minus a by 2, a by 2. This will be sine of 4 pi by a x dx. Now we can see, we can integrate this as well, but we can clearly see that this is sine and it is between the limits between minus a to plus a by minus a by 2 to plus a by 2, and we know this sine is an odd function. This is an odd function. We will use that property and we will simply say that this integral between the limits, symmetric limits, minus a by 2 to plus a by 2 sine of 4 pi by a x dx is equal to 0. So what we got? We got the average momentum along x to be equal to 0. Now let us see which option it was. It is the option A. So we are going with option A. Now if we see the average momentum, it was 0, and we have got the solution, the desired solution. Now we are left with the last problem of the assignment 1. So it states that if we have a particle which is of mass m and it is moving in one dimension with a potential which is given by a times delta of x between the limits x and it is infinity elsewhere, and we are required to find the value of this a for this, for the ground state energy to be equal to 0. We know that if we write the Schrodinger equation itself, and we will use the something the symmetricity of this potential as well. This is between a and minus a, and this is at 0. We know this is infinity elsewhere, so we will use the Schrodinger equation minus h bar square by 2m d square psi d square x d square x d by d square of x psi plus b psi equal to e psi. It will simply be, since we have been told to find this solve the Schrodinger equation, we take this reference, potential reference, to be equal to 0, and also this energy has been mentioned to be equal to 0, as it states that ground state energy has to vanish. So we are left with simply minus h bar square by 2m d square. Let us write it to be psi d psi by dx square equal to 0. Now if I simply integrate it once, I will be left with d psi by dx. We know for a constant the derivative is 0, so if I integrate it, it will simply be some constant b, and now if I integrate this again, it will be psi will be given by some function b of x plus some constant c. Now if we see we have some properties for the wave functions, that if a wave function uh, this we know that this is infinite outside this a, this outside this a, this wave function will not exist, so we will be having the psi of x of a equal to 0. It simply says that this wave function has to go 0 at the boundary x equal to a, and this function has to be continuous. That's why it is 0 at x equal to a itself. So we can use this boundary condition and we can put it in equation number 1. It will give us to be equal to 0 equal to b times a plus c, or we can get c equal to minus b a. So this is simple. The function, the psi in the limit interval of x will be given by if this x is less than a but is greater than 0. Now we see this potential is symmetric, or we can do the integration again, but it will give us the same value for the wave function, it will come out to be, by replacing this by minus x simply, it will be minus x minus a for x less than 0 but greater than minus a. Now we know that this wave function, this has to be continuous at everywhere, and we use that boundary condition at x equal to a. Now we will be using that boundary condition again at the uh, x equal to 0. We will simply solve this Schrodinger equation again. We will say that if we are now left with this minus h bar square by 2m, between the limits, we are integrating the Schrodinger equation between the limits 0 minus plus 0 plus, we are tending towards this 0 from this direction and this direction. So minus h bar square by d square psi by dx square. This is the kinetic energy part of the Schrodinger equation that we are integrating, and the other part, which is the potential part, which comes from the potential energy 0 minus plus 0 plus, and it is given the potential is a times delta x, a times delta of x. Psi of x will simply be equal to uh, dx equal to integral of e psi of x between the limits 0 minus to 0 plus. But we know this e has to vanish, this e is equal to 0, so we are simply left with minus h bar square by 2m limits 0 minus to 0 plus d square psi by dx square dx plus 0 minus to 0 plus a times delta of x psi x dx equal to 0. Now if I use the property of delta function, that is, if I use 0 minus to 0 plus, I know delta of x f of x dx is simply equal to f of x at x equal to 0, and I will put the integration limits in this as well. It will simply be equal to minus h bar square by 2m psi dash of x tending to 0 plus minus of psi dash x tending to 0 minus, and it will be equal to plus times a times psi of x equal to 0. This will be equal to 0. Now if I simply put this x tending to 0 for the case over here, I will be left with b, and if I put it over here extending to extending to 0 minus, I will be left with minus b. So it's simply, I will be putting these limits and I will get it to be equal to minus h bar square by 2m b of minus b equal to, it will be equal to minus a, and this c, I will be putting x equal to 0, it will be minus ba, and it will simply be minus of ba, and I will cancel this minus and minus, it will be 2b h bar square by 2m, and it will be minus ba a, or this b and b will go, This 2 and 2 will go. I will be left with minus h bar square by ma, and this is the value of this a. So we have seen that the answer to this problem is C. Uh, I think it's already 6 and we have covered all the problems from the assignment 1, and in next live session we will be starting with the assignment 2. So if you have any questions, you can put them in the chat box, or if you don't have any question, you can leave the session so that we will end the session.
Hello.
Uh-huh.
It was a nice session, sir.
Oh, thank you, Lakshmikanta. You can leave, Lakshmikanta.
Thank you, sir.
Thank you.